Okay. So yes, is the rest frame of the universe universal? It's a strange question. A little teaser is the background image. This is a 1 steradian smooth map of the radio sky of source counting. And so you see there's a little hint there of an interesting signal. So the cosmic microwave background dipole, we all know about this. There's a hot direction in the universe and a cold direction. We see this dipolar pattern, and the interpretation is that we're moving with respect to the rest frame of that early universe. The motion's about 370 kilometers per second, but I like to think of it as 80 astronomical units per year. So we're cruising along at 80 AU per year through the universe. Okay, and the question here is, what this suggests is a universal rest frame that should be shared by galaxies. So everything between us and the CMB, of course, we're just looking back through history, so there should be this single rest frame for the universe. And so what I'm going to show you are 3 different things galaxies should do if this is the case. So we'll ask, what should galaxies do? The first thing they should do is show a parallax. So we're cruising along at 80 astronomical units per year. This will create a secular parallax. Okay, so it will look like galaxies are streaming from the direction of our motion and converging behind us. So it's sort of like jumping into warp speed. Okay, but it's very, very slow. But if we remember the definition of a parsec is defined by an arc second, AU looks like an arc second from a distance of a parsec. Okay, and so 80 astronomical units per year equates to 80 microarc seconds per year for a distance of a megaparsec. So if I look at a galaxy a megaparsec away, I'll see an 80 microarc second per year motion. So it's small. And that distance, that parallax is inversely proportional to distance. And what I'm showing here is not a measurement, it's a forecast, but using a real catalog of nearby galaxies, you see what this signature should look like. This is done by Jenny Payne at the University of Colorado. And what I'm going to do is tinker with that equation a little bit. I'm going to change the distance out for Hubble's law. So we can write this as CZ over H naught. Okay, rearrange the equation. And we have an expression here for the Hubble constant that depends on measuring the parallax and the redshifts of galaxies. So if I can measure redshifts in the secular parallax, I've made a geometric measurement of the Hubble constant. As you can imagine, for nearby galaxies, though, there's a problem, which is peculiar motions. So there's peculiar proper motions due to large-scale structures. And it turns out that they are very similar to the expected parallax. The parallax is the y-axis. Peculiar proper motions are on the x-axis here. So they're quite similar. We think we can disentangle these things. We haven't done it yet, but I think it will happen pretty soon. So we expect to be able to detect that secular extragalactic parallax and disentangle it from the motions due to large-scale structures. Okay, so that's item 1. That's what galaxies should do. What else should they do? Well, as we've seen with the CMB, there's a red-shifted direction and a blue-shifted direction. Strangely enough, the CMB folks like to indicate blue shift with red. Okay, hotter, I guess. So you'll see a little discord here with the names of the colors and the actual colors. But in any case, the direction we're moving, we'll see a blue shift, and the opposite direction, we'll see a red shift, okay, for galaxies. So that's what we should see. The other thing we should see is relativistic beaming. So in the forward direction, we should see things getting squashed and compressed. And in the rearward direction, they'll get stretched, okay? So if I'm squashing and compressing my view of the universe, I should see more galaxies in the forward direction and fewer galaxies behind me. So we should actually see a change not only in the color of galaxies, the red shift and blue shift, but also the number that we see on the sky as a function of position on the sky. Okay, so that's our relativistic beaming. So the problem is that studies of the dipole in galaxies in AGN are mixed, and some agree with the CMB, but a lot show significantly larger amplitude, particularly when counting galaxies. Okay, so what's happening here? Here's a little selection of very recent work showing on the left the range of velocities that have been measured. The CMB is the vertical line on the left, and you'll see there are some significantly larger velocities inferred from counting galaxies. On the right is the apex of those dipoles that have been seen on the sky, and the center is the CMB direction, and the size of the point scales with the velocity that's measured. So you see the big points are sort of offset from the CMB apex. That's mostly galaxy counting once again. All right, so previous work, as I said, has disagreed with the CMB, favoring large velocities generally when galaxies are counted, including quasars and radio galaxies. However, other work does agree with the CMB, including clusters of galaxies, redshift arrays, and supernovae, so it's a little confusing. All right, so what I'm going to do is show you how this works. Then I'll show you an example of doing this counting of galaxies using radio sources. And I'll first show you how to do it incorrectly, which is how I did it. And then I'll show you how to do it correctly using the ngVLA and SKA. So let's talk about relativistic Doppler shifts. We said there's a blue shift in a red shift direction. There's a dipole in the sky caused by our motion. This is just normal Doppler shift. And the main point here is that, there we are, what we see is there's a Lorentz factor gamma, okay, and it's modulated by cosine theta. So you're going to see cosine theta a bit in this talk. What this means is that in forward direction, that's theta 0. As I move away from the direction of my motion, I modulate the sky, in this case, the Doppler shift, as I walk around the sky. Okay, so every time we see that cosine theta, that's my dipole. Okay, so we're going to see this delta, which is that dipole. We're going to see multiple powers of this as we walk through the different effects. So here's the relativistic Doppler shift. We get a blue shift in the forward direction, red shift in the reverse direction in a dipolar pattern. Okay, the other thing we talked about is relativistic beaming. Angles are compressed in the forward direction, solid angles. Okay, so we get a factor of delta squared, but instead of getting bigger in the forward direction, they get smaller. So we have delta to the -2. Okay, so we get a compression in the forward direction, smaller angles, so we get a higher density of sources. And the other thing that happens is if I do a flux limited survey of the sky, it's not flux limited anymore. Okay, it's not uniform, I should say. Okay, so in the forward direction, there's a boost. Okay, I get relativistic beaming, so objects actually look brighter and bluer. Okay, so there's two effects here, is that my flux limited survey across the sky is no longer uniform. In the forward direction, I actually see fainter sources. In the rearward direction, I see brighter sources, or my flux limit is higher. Okay, and so what we worry about is both the slope of the number distribution versus flux. That's what's shown in this plot. So if I have a slope of x, that will come into play. So I'll sort of walk down that distribution of objects in the forward direction, see fainter ones. What also matters is the spectral index of sources. So we'll call that alpha. And so the number density of sources will show a dipolar pattern once again, that factor delta, but to some power that involves both the spectral index and the distribution of sources. Okay, so here's a prediction putting all of this together, and we use small v over c. Of course, we're talking about 300 out of 300,000 kilometers per second. And what we see here is that dipole, there's that cosine again. So we're going to see a dipole pattern on the sky in terms of the number density of sources. And when I do this for radio sources, I use a spectral index, a typical spectral index, and the slope of that distribution. I get a expected amplitude of that dipole of about 0.5%. Okay, so it's a 0.5% type measurement. If I want to actually make the measurement, say at 5 sigma, I need to get down to 0.1%. Okay, so I need to get my systematics and my uncertainties down to a part in 1,000 to make this measurement. Okay, so we're very worried about systematics. You can do the same exercise with total flux, so I can just add up all the flux in the sky and look at how that's distributed, and we see basically the same thing. So I can count number of galaxies or just add up all the flux in galaxies and look for this dipole. But I have to get those systematics down to 0.1%. Okay, so I'm going to show you how to do this incorrectly first. But radio is very good for this type of activity of counting galaxies. This is really basic, we're just counting stuff, right? But radio is very good for this because I want to maximize the sky coverage. I'm looking for a dipole. This is a big signal on the sky, so I want to get as much sky as I possibly can. And that also means that I want to minimize the impact of dust so that I can exclude only a small part of the galactic plane. And I don't want to have strange dust gradients as I look with galactic latitude. So radio is great for that. The other nice thing about radio surveys is it is typically selecting for me higher redshifts. Okay, so I'm less subject to local large-scale structures causing bulk motions that will give me some sort of other dipole. Okay, well, that's what we saw when we were talking about the peculiar velocities at the beginning here. So what I did, just to show you an example of how this is done, I did this last year. So I took 2 surveys, so I need to cover the whole sky, but we don't have radio observatories that can do that, so we have to combine hemispheres. So I combined the VLA sky survey at 3 gigahertz with the rapid ASCAP continuum survey at 0.9. This is a bad idea, okay? 2 different frequencies. But in any case, one does one's best. And so there's an overlap region between these two surveys where we can try to deal with those systematics and try to reconcile the two and align them, even though they're at different frequencies. Okay, so here's a map of the sky, just counting galaxies in 30,000 pixels, combining those two surveys, omitting the galactic plane and the poles, the equatorial poles. And so here's what we have. Now, if I just take something like this and I smooth it by a steradian, what do I see? So this is counting galaxies. I'll show you a smooth flux maps. This is the flux of galaxies, radio sources. And you can see there's something interesting going on here, just a smooth map. If I fit a dipole to, say, the number distribution, here's what I get, plus or minus 330 kilometers per second. Remember, the CMB is 370. Okay, so that's nice. However, the uncertainty on this is large. So here's a bunch of different methods to measure that dipole. The top row is number counts of these radio sources. The bottom is flux. The left is the position of the dipole apex, and the right is the velocity. And the vertical bar there is the CMB velocity. So you see all these different ways of measuring are consistent with the CMB. The error bars are huge. Okay? These measurements are also consistent with some of the previous discrepant measurements, just because the uncertainty is so large. Okay? All right, so what this is showing us is that using VLAS and RACs, we find that galaxies share the CMB rest frame. This measurement should improve with time because these are really early preliminary continuum surveys. There will be more epochs with the VLA, and of course, there'll be deeper surveys in the south. Problems with this are merging two surveys at different frequencies and resolutions, of course, and the source multiplicity is frequency dependent. Okay, so I try to reconcile these two surveys, but as we know, when you go to higher frequencies, things break up into little pieces. Okay, so the sample's too small here. We need a larger sample. This gives us large uncertainties and does not resolve the disparities. So what should we do? How should we do this correctly? The solution is we need a uniform all-sky radio survey. Once again, we can't do that. We need two hemispheres. But if we do overlapping hemispheric surveys, we want to overlap them both in frequency and spatially on the sky so that we can reconcile the two and deal with that part in 1,000 systematic. So we need large and high completeness and matched resolutions. So the prediction here I'll make for using the ngVLA and square kilometer array continuum survey, imagine that we did a fast continuum survey for both hemispheres, overlapping in frequency, somewhere between 1 and 5 gigahertz, overlapping at the equator, so that we have a nice piece of sky where we can reconcile the two surveys and deal with our systematics. So I'm going to scale empirically the results I just showed you to such a survey. So if we do that down to about 30 microjanskis, we'll get about 100 million sources, and we expect to detect that dipole as a signal to noise of 30. That's 12 kilometers per second uncertainty in the velocity and 2 degrees in direction. This agrees with previous theoretical predictions, roughly, that do not include large-scale structure issues. This sort of does implicitly the empirical scaling. So in any case, if we were to sort of reproduce this using the ngVLA and SK combined, this is really the way we can definitively address that galaxy dipole issue, both in flux and number. We'd need an all-sky radio survey with about 100 million sources. And we'd be able to assess that dipole versus redshift, because remember, the uncertainty in velocity is about 12 kilometers per second. So I can actually slice and dice this sample and look to see what is the impact of large-scale structure at different redshifts and for different subsamples, which is really important to do. The last thing is that figuring out this dipole, what's going on here, why are we getting these strange answers, is essential for that extragalactic parallax interpretation. So if I'm going to say, observe parallax, extract the Hubble constant from that, I'm relying on the fact that the galaxies share the rest frame of the CMB. Okay? So I'm relying on this galaxy count dipole being correct and agreeing with the CMB in order to do that parallax and H0 measurement. All right, that's it. Thank you.
Excellent. Any questions? Go over here first.
Yeah, lovely talk. As you mentioned, the systematics are a big problem here. And the one that I worry about in this field particularly is that you're doing these observations with interferometer, right? And by nature there, you are missing flux regardless of what interferometer you want to use, and you resolve out structure, for example, with VLAS and stuff like that. How do you get a handle on what you're missing there, right? Even in the source counts and the total flux with the interferometer with these types of measurements?
That's right. So I worry more about it with a flux measurement than with counting. Counting though, so what one does is basically, you may have seen this in an earlier plot, is that we are well above the completeness limit. So you don't sort of work down near the completeness limit. That's just a recipe for trouble in terms of counting. Yeah. So that's the main way that we would address that. Trying as much as we can to match resolutions of the two hemispheres is also key. But of course you can fiddle with that. Yeah.
Okay, thanks.
We'll go Tom, and then in the back.
Yeah, how much progress do you think you can make with existing data if you bring the V-light part of the VLAS into the mixture?
We might be able to improve uncertainties by a factor of 2, maybe.
Thanks. Oh, yeah, thanks, Jeremy, for a great talk on systematics. By the time you get that deep in your proposed survey, I think you're now mixing two source populations, yes. AGN and star-forming galaxies. How do you handle that?
Absolutely, yeah. And the answer is 1, I don't know. But 2, yes. So, and the other issue is that once I start going deeper, I'm bringing in a different population, but it's also at a different sort of average redshift, right? And the galaxies I really want to exclude are local. So less than redshift of say 0.05 or 0.1. However, I think just even with photometric redshifts, one can do a decent job of excluding that population.
Jeremy, thank you for the talk. So I was wondering, you must have tried this. What happens if you don't try to combine the two surveys and just deal with VLAS?
Yeah, it's a great question. So we know that both of these surveys are more than a hemisphere. They extend beyond the equator in either direction, okay? But what they both show is a gradient in their sensitivity versus declination, okay? And so and they also, you're not covering as much of the sky, okay? And so what happens so a theorist would say, oh, that's fine, you can measure part of a dipole. If you measure it well enough, you've got the whole dipole. In practice, what happens is that the dipole apex likes to run to the place where I have no data, okay? And I'm basically measuring the waist of the dipole and can have a huge amplitude. And that's my concern with these previous surveys, is their sky coverage fraction is like 60% or 50%. So that's the issue. So I will say that, of course, I've tried it with just, say, VLAS, but that declination gradient causes us to get a very strange dipole fits.
All right, Brian's going to ask a question from online.
So this is a question from Catherine Hale. Do you think the declination effects would play, let me start again. Do you think declination effects would play a big issue in systematics, which may not be different in overlap regions?
They do, for sure. And so one concern is that, yeah, the overlap region of, say, two hemispheric surveys, I'm sort of reconciling them in a place where I may have systematics for both. It's a problem.
Take one more question.
Does the intrinsic velocity of the emitting region matter? So following up on the AGN versus star-forming galaxies question, if you're adding 300 kilometers per second to something relativistic, is that different from adding 300 kilometers per second to something that's just moving?
So with this sort of measurement, there are lots of things one worries about, but as long as that effect impacts your sample in the same way across the sky, you're good, okay? So even if I said, 10 different weird populations of radio emitters, but they're uniformly distributed on the sky, then I'm okay, right? So one always sort of has to rely on the cosmological principle that what's weird things that are happening in one hemisphere are also happening in the other.
Excellent. Let's thank our speaker again.